Hello Internet, and welcome back to our weird pixelated 3D mesh shader thing. I really need better names for things because I don't know what to call this. It's sort of marching cubes, but it's definitely not any. It doesn't do the algorithm at all. This is just rounded pixels or rounded vertices. This is broken, and so what we're going to be trying to do is fix the lighting right now. There's a number of issues that arise from that that we're going to talk through. This is probably going to be one of those weird rambly videos because I don't actually know what I'm doing here. So who knows? This could be something that takes like 20 minutes, or this could be something that takes closer to an hour. If it goes any longer than that, we have problems that are beyond the scope of one video. But hopefully this is something we can do relatively quickly. I think we can use some of the code we've done in previous projects to actually accomplish the same thing. There are some downsides to this. As far as I know, surface shaders do not support geometry shaders, and that is what we're going to be using to fix the lighting. And so what that means is we are not going to be able to use this nice lighting that we have right here. Instead, we're going to go back to this thing. That's not how you do that. This thing. This doesn't look nearly as good. This is just our original implementation of this. This is using a vertex and fragment shader. So if you're unfamiliar with the difference between those, I think we've already covered that in the series. But anyway, if you're unfamiliar with the difference between them, surface shaders are Unity's wrapper around vertex and fragment shaders. They do a lot of really cool magic in order to integrate with all of Unity's lighting systems and other features. Vertex and fragment shaders don't really do that. That's why this is unlit. There's no lighting here. This is the default if you go create shader, unlit shader. That's what you're going to end up getting, is a vertex and fragment shader. It's called a vertex and fragment shader because one does the vertices and actually positions those in space, and the other positions the fragment. The fragment is effectively a pixel. They're called fragments because technically, because you're drawing multiple objects, you can actually draw the same thing over in more than once in a pixel. So that's how that goes. Anyway, that's kind of tangential. We are going to try to do this with a geometry shader. I showed shading wasn't working. So what I would expect is like this 4 faces here, these 2, and then these 4 there. Those should have consistent lighting because they're all facing the same direction. They might have a little bit of fall off because they're slightly in different positions and there's an angle difference, but not really. So seeing this like jarring cutoff is not what we expect. And the reason that that's happening is because we are just moving these vertices around, but we're not changing all of the data. We're just changing the data about the, what's it called? We're just changing their position in space. We are not changing like the direction they're facing. There are a few reasons that we want to use a geometry shader instead of just trying to fix the normals normally. Anyway, the reason we want to do that is because there may not actually be enough information for us to actually do what we want. In order to get those hard edges on the sides, what we're actually doing is, what's the word for it? What we're actually doing is changing the geometry, I guess, of this thing. So we're trying to create a flat geometry or shader, I guess. So you can actually see these sides, because that's sort of the point of this, is to create these like harsh linear sides. And so because those things are aligning to a grid, the normals that were encoded into the mesh are not accurate. This is supposed to be a sphere, so we have normals pointing in every direction. And the intention is that when you interpolate between those, you get something that looks something like a sphere. But here, what that's actually causing to happen is we now have the normals on these 2 faces on the bottom parts of this facing in a different direction than the top part, and that's causing the lighting to be calculated differently. So that's what's causing this. I'm not entirely sure why we get these big squares. I think that's because of the vertex rounding again. So we're things aren't really accurate with the way we do this. If we try to apply meshes or if we try to apply textures or something to this, they're going to be stretched all over the place because we're completely moving things and we're not adjusting for that. We'll fix color in a later video. I think we might be able to do something about that, but not now. Anyway, the idea of a geometry shader is it allows you to create additional geometry. It's going to fall after the vertex shader, but before the fragment shader. So after we have snapped everything to a grid, what we can actually do is take a triangle and actually recreate that triangle as a new mesh. So the advantage of doing that is we can give all the triangle or all the vertices in that triangle the same normal, which means they're all pointing in the same direction. So instead of like a normal circular spherical mesh where every vertex is kind of a slightly different angle, so you get that smooth lighting effect, here we're actually going to be removing that. We're going to try to take that away and create something that is fairly flat. So we get a consistent lighting effect across these similar surfaces. I think a geometry shader is the best way to do that. I'm not entirely sure though. So if you have ideas, let me know. But we're going to do a geometry shader today. So yeah, that's where we're going to start. This is the slightly modified version of our rounded vertices shader. I did not go and implement a world space version of this. But I have now. So I've done that behind the scenes. This is the two changes I made. I can get rid of that. But basically, we move the thing into object space or into world space from object space. Your vertex shader is going to be past the object in object space, so relative to itself. And then we need to translate that into world space. That's where our grid is. We do our grid calculations here. And then we're actually going to expand that further. So in order to the end results, I guess, of a vertex shader should have gone through a model view projection matrix. And so we haven't done that if in the no other one, we're just giving back a object space. That isn't going to work for us. But here we need to give a projection modified mesh vertex. Yeah, words are hard. Anyway, in order to do that, we don't need to go back. So we don't need to go back from world space to object space and then do the projection. We can actually just continue the transformation. And so in this case, we're doing the model matrix. That's what's being modified or multiplied here. We get into world space, do all of that, and then we multiply by the view and projection matrix to get the whole thing. So that saves us a few steps. I think that's pretty much everything. There isn't any other modifications I had to make, I don't think. I have some notes over here, and that we're going to rely on those because pretty much we're doing the same thing. I'm going to just try to hopefully make this make sense. There's a lot of changes that we're going to make, and I'm going to try to do them relatively fast just to kind of keep things moving, but we'll see what happens. If you're unfamiliar with all of this code, go and watch the first video because that's when we implemented all of this, except these two lines. So anyway, what we want is to create a geometry shader. We have vertex, we have fragment. Geometry shaders are the same thing. So if we want to do that, we can just do what? Okay, weird. IDEs never seem to get this shader syntax. They just can't handle formatting it for whatever reason. So we're just going to define there's a geometry shader and its name is going to be geom. We're just going to use something short and it's going to go somewhere in here. What that's going to look like is this. I'm just going to copy this because I am not going to remember that. But it's going to look like this. So what we're saying is there's going to be a max number of vertices that come into this, 3. And we're going to give a triangle into this. So we are passing in triangles into this geometry shader, and we are going to convert those triangles into another triangle. Effectively, we're just going to modify this triangle stream and start putting new things into it. And so basically what we need to do is, given a triangle, a set of an original triangle, we need to return a new one. And that's what this geometry shader is. That's the whole point of this. This has a reference to a V2G, and you'll notice that doesn't exist. It also has a G2F. That doesn't exist either. But you'll notice Vertex, our Vertex shader, has a V2F, and that's used here as well. What's happening there is we actually have objects that are effectively data transfer objects intended to move data from one of these functions to the other. In this case, V2F is vertex to fragment. We're not doing that anymore. That's not happening anymore. Instead, we need to move vertex to geometry and geometry to fragment. So hopefully that makes sense. And effectively, we just need to store in these two data structures the data that we need to send from one to the other. So V2G is going to be the data that is going to be required by our geometry shader in order to do whatever calculation we're telling it to do. And then the G2F is going to be whatever is required in order to actually do this fragment calculation. That's how all of that's going to work. I have templates for these, so we're going to use those because they're already done. And that just makes a whole lot of sense. So I'm going to paste these here. These are straight from our straight from the code for our lit shader demonstration. So that the flat shaded demonstration. I don't know what I meant to call it, but anyway, that's what that's from. Position. Why did I call it position? Let's just call it vertex. Cool. And there we go. I don't think we're using app data. App data, is it used? It is used. Okay. We pass in our vertex there. Then we can probably just use position. Position will be fine. So there we go. We have position, we have a normal, we have a UV, and a color. And then we have a position, a normal, and a diffuse color. The diffuse color is just whatever color we're going to use. Anyway, basically we're plugging these values in. These color coordinates are going to be things like the color at a vertex, or the UV at a vertex, or the normal at a vertex. The normal, actually, I don't think we need to pass in. We may be able to just skip that entirely because we're going to be recalculating that. So that's the whole point of this, is to calculate that normal position. To do that, we're going to be using cross products. We will get to that in a second. But these are the three things that we need to use. In this case, the way this whole thing is working, app data comes in to our vertex shader. Our vertex shader does some numbers and does all the vertex snapping things, and then sends that over to the geometry shader with all of this information. And then our G2F is plugged in after the geometry shader has done its calculations and goes to the fragment shader, which does its final thing and then tells the computer what to draw. So at the end of this, we're going to be drawing whatever's in here. That's going to be our paint by numbers, do the stuff. So hopefully all of that kind of connects. It should be everything we need. We do need a bit of extra information here, and that's wrong. That needs to be changed to a V2G. We have our vertex and we have our UV. The problem is it's no longer called vertex, it's called a position. So we're just going to change that in the output. And we have a normal and a color. And I don't think we're doing anything with it. I need to quickly check. We're just pulling in random information. Okay, we don't need any of that. So we're going to drop the normal and we're going to drop the color for now because we don't need it. We could actually probably drop the UVs as well if we wanted to simplify this even further, because we're not going to be using them. We are not reading texture information, and that's what UVs are used for usually. So G2F, we're going to pretty much do the same thing. I'm going to keep the diffuse color because I think what we're going to want to do is calculate the lighting in our geometry shader, because we'll already have the normal and we do not need to recalculate the lights for every single fragment, I don't think. There's some downsides to that. Perspective is going to be slightly different if we start doing that kind of thing. But if we're just comparing it to the light and not to anything else, this should be fine. So that's what we're going to work with. Won't work for like specular stuff or anything, but by passing this in the diffuse color as like our lighting strength, I guess that's what we could call it. Sure, let's just do that. Let's call it float light strength. I don't know what we're gonna do. I think I can just do this and then we can just get rid of this one. I'm making this up, deviating from all my notes because I'm thinking about things. I think this makes sense. This way we can pass in a color up top and do some things in the fragment shader. I don't know why we'd want to do that, but anyway, that's an option now. Great. Cool. All right. All of that output is good. We should get it into our geometry shader. Our fragment shader should be able to do stuff now. It has access to... It's trying to read a texture. It's not going to be able to because that isn't a thing anymore. It's trying to do fog. We're going to just delete fog references because no. And what else? Speaking of getting rid of fog, let's just get rid of that because I don't want to deal with it. And the shorter we can make this, the better, I feel like, because geometry shaders already get weird. So light strength is what we're going to be using. And so the input here is just going to be color equals our, I believe we have a color here, and I'm just going to multiply that by I times light strength. And that should be our color. So this way we can tint our object whatever we want. We can make a red thing, and it should still be shaded because it will be multiplied by the light strength. That's effectively how we're going to do this. It's not great. You can go much further with your own custom lighting. We are not doing a lot of that because all of that is just going to make this more and more complicated. There are examples to get close to standard shader effects, but we're not dealing with that. This is mostly going to handle like a single directional light as your light source. If you start adding additional point lights and things like that, this isn't going to work, and I don't think it's going to work in deferred rendering either. There's differences between forward and deferred rendering if you're not familiar. The technologies work entirely differently as far as how lighting is done. And I'm not entirely sure how this would be handled. So that's honestly not something that I've worked with a lot. So anyway, we're going to ignore it because then I don't have to deal with it. If that's something you care about, then you're going to have to go and read about it. Sorry, I can't be more help. Anyway, where were we? I'm going off on tangents, and I hope they're useful, and I'm worried that they're just confusing. Anyway, that's good. Let's create a triangle stream. So the triangle stream is just going to store a bunch of triangles. We just need to push triangles onto it. And so in order to do that, I'm just going to copy one of these. This is how I push a triangle to it. This pushes a single vertex to it, so we need to do this 3 times. But what it's doing is taking the position, the input position, and multiplying it by the model view projection matrix. We've already done that, so we don't need to do it again. So this can be tweaked. Again, this is directly from the flat shader tutorial I did a few years ago now. So we're kind of basing it off of that, but we do not need to do this. This part isn't needed. We should just be able to reuse the position information because we've already calculated that. This index is going to change for each of these, and the normal is going to be calculated. So basically what we need to do, we have light strength, which we're going to need to calculate. That's going to be a dot product, and we can do that once we have everything else. But that is pretty much everything we need. So we need to calculate a normal, and we need to calculate a light strength. Those are going to be different, or those are going to be the same for all these. So basically, the only thing that's changing is the position. Light strength and normal should not change. So there we go. 0, 1, and 2. That should handle our entire triangle. Now we just need to actually work with this thing. So in order to get the normal, we can use the cross product. How did I do this? Float 3, normal. And we're going to normalize. Yeah, that's not how you do that. Normalize the cross product of two vectors. So if you're unfamiliar with what the cross product is, given two vectors, it will give you one that is tangential to that. Is that the right word? Perpendicular. Is it perpendicular? I don't know. If you do like the right hand rule thing where you have your fingers kind of creating a vector, you have X, Y, and Z. If you're given two vectors, so you're given X and Y, for example, the cross product is going to give you that Z vector. This changes if you're doing left or right hand rule math, and I don't remember which does which, but that's how we're going to be getting our normals. Because we have a triangle, what we can do with this is actually take the 3 points of our triangle and draw two lines between them, and those are our two vectors. And then if we calculate the cross product, we're either going to get a vector going into our mesh or out of our mesh. It doesn't really matter which one, because if we get it wrong, we can just invert it. But that's pretty much how we're going to calculate this lighting. So basically, by doing this, we should be able to convert the flat triangle plane, which is effectively what that is, and get some upward facing vector that we can use to calculate lights. So in order to do that, what math did I use? I used V0 minus V1 and V1 minus V2. And that's pretty much it. I pulled out those vectors like this. And I guess we're just going to copy and paste it because it works. And it doesn't make a lot of sense to redo it. Plus, this code actually is fine. So basically, we're just taking the input position, the XYZ vector, the position in space, and using that to calculate what the actual normal of these faces should be. And then once we have that, we need to calculate a world normal. And that is going to be float 3 world normal. I can copy this too. We can actually just do a multiplication of unity object to world. Is that correct? I think so. So this normal is going to be an object space. That's the name. So that is object space. Is it object space? No, it's not. Oh, this could be interesting. We may need to rethink this. Or I need to go backwards. So there's some problems here. We're in the projection space. And I just calculated the normal in that space, in the projected space. Problem with that is not going, our light is in world space. And you can't really compare things that are in different spaces. It's like talking to somebody and telling them to go right. They're going to go a different way than you were, especially if you're facing them. So it's not going to work. So we need to actually get everything into the same coordinate space in order to do this. The best way to do this may be to cheat. I don't know if this is the best solution, but we can actually just set the position equal to the vertex here. So our vertex is what we calculated, and then the position is what's being passed to our geometry shader. We can take this calculation. There we go. And so now these are in world space. So these coordinates the triangles are all provided in world space. Then the geometry shader can output our positions into the correct space. Does this make sense? I think it does. Means we're doing slightly more work. And this is the part where I said these things could get complicated because this isn't always straightforward. But what this means is that V0, V1, and V2 are world space coordinates for the 3 vertices of our triangle. These positions, these output positions, are going to be in our projection space. So we can't use them interchangeably, but we have the reference to the world space thing. And it shouldn't matter that I modified it like this. I don't think. Little hesitant there. I'm not entirely sure what the side effects of doing this are. So things may behave poorly. And one of the downsides of all of this is we haven't tested anything, which we should be able to do. If I've done everything correctly, this should still render exactly the same thing that we already had rendering, which isn't actually useful. It is not. We have a syntax error on line 65. Looks like we forgot some semicolons. Yes. All right. So add those in and recompile this and see what happens. Still doesn't like it. That's fine. I'm actually going to apply this to our material so we can actually see it. We get the purple shade of death. That's fine. Multiplication on 65 and 70. Oh, well, that's not going to work. We're multiplying this by something that doesn't exist. We did not need to do that. This normal is a world space normal. So we actually do probably want, do we? I don't think so. I don't think we need to, because we really, in order to calculate the light, we just need the world space normal. We already have that. These are all world space coordinates. So this should be fine. We don't need any additional calculation. So that should work. Light strength at line blah. That's not defined, so let's just define it. Light strength equals 1. Cool. Redefinition of out. We don't need that. So what we're doing is we're creating a single variable and then we're reusing that variable reference. I don't know if that's best practices. There are some gotchas there. If we do not reset all of these values, like if we go in and delete one of these lines, weird things might happen. We actually probably can because they should be the same. But there's a gotcha there. Undeclared identifier color. So there is no color? No. Well, that's annoying. Let's add that. Color. Sure. The color. And we're going to choose white. That's not how that works. This is a... Yeah. This is a 4-dimensional vector. So red, green, blue, and transparency of the alpha channel. So that is our color. That defines it for unity. We need to create it down here. So we'll just add it in here. Float floor color there. So now we have color. This needs to be 6-4. Okay, it's fine. So there we go. Does this work as I move it? Yes. Is it correct? Appears to be. So because it's snapped to 0 coordinates, we should expect like triangles, and that's what we see. So that is the expected output. So we're getting the right thing. It's still changing as we move it, so it's still in the world space grid. So everything seems to be fine. We haven't broken anything, but we haven't actually done anything. None of this code we've written has done anything. It's just made our GPU do more work, which is great. But all of this is just kind of getting to the next part, which is the fun part. Really, all we're trying to do is solve for this light strength. That is the point of this. So we're calculating all these normals so that we can calculate a light value. So we're going to move that below so that we can actually calculate it in the right spot, and actually start doing things with this. So in this case, our light strength is equal to 1. That is not always correct. What we want to do is reference our light position, which is in something. There we go. There's a light position. Awesome. So this is the light position. In order to get this from Unity, we look at this. This is the world space light position. This is going to be a vector facing in the direction of the light. So this is the directional light in your scene. If you had a sun or whatever, that's what this is. If you had multiple, this is not going to see any of those other ones. So that's the side effect of this. But this gives us the first directional light in your scene. And so we can use that to calculate lighting effects. So we want to do that in the light strength. To do this, we use dot products. If you are unfamiliar with what a dot product is, think of it as the angle between two vectors. And what it's going to do is effectively give you in radians, is it radians? No, I don't think that's a good way to describe that. Basically, if the two things are in the same direction, you get 1. If they're in opposite directions, you get 0. If they are perpendicular, I feel like I'm not using that word correctly, but maybe I'm just paranoid. If they're perpendicular, so they're going in two different directions at like 90-degree angles, then you're going to get 0. If they're in between that, you're going to get some angle that represents the cosine between those two. So two angles in the same angle or direction as one another are going to have a cosine of 0, or cosine of 0, which evaluates to 1. So that's how all of that works. This only works on normalized vectors. If they are non-normalized, you're going to get some values that exceed or are below 1 or -1. So what we want is between 1 and -1. So that is why this normalizes here. That makes sure everything is sort of in the same thing. This vector should already be normalized. If it isn't, then other things are screwed up, and I don't know what to do with that. But we have two normalized vectors, and we want to compare them. And then we're going to effectively use that as a way to judge how bright or how much in the light is this object. If it's directly facing the sun, then that is 100%. It's a 1. If it's facing the exact opposite direction, then that is 0. We go from 1 to -1, so we need to do some trickery in order to do that. So we're going to do dot world space light pose 0. We stored that in light position for a reason. So dot of light position and the normal. So this is comparing two world space normals against one another, and we're going to get a value between 1 and -1. So what we're going to do is add 1 to this, and then divide it by 2. So what this does is we have -1 to 1. We shift it up 1, so now we have 0 to 2. And then we subtract that space, so it goes from 0 to 1. And this gives us a lighting thing. This isn't going to be the most realistic lighting that we could do, but it should be enough to kind of get the point across. Yes, awesome. All right, that was the point of concern. I'm not sure this worked exactly how I wanted, but I don't know where my light source is. So we're going to go and find that and move it up here. Go. That actually might be correct because my light source is in a weird direction. But we actually have lights and they're correct. And you can see as we move things actually get calculated, and the faces that are facing in the same direction look the same. That is what we wanted. That means that this is for the most part, actually doing what we want. So that's good. It actually makes this effect look significantly better. We lose a lot of the fun Unity lighting stuff. There's no skybox, there's no specular lighting, all of that. That would be extra. That'd be stuff we'd have to add on top of it. But if we want just basic lighting on this that actually works, this accomplishes that. And that's what we wanted to do. So I think this is a fairly successful way to do this. I will try to share this code. Hopefully it's enough. I'm going to tinker with this a little bit before I end though, because I think we can drop these and do that. And so this way I can do that, initialize the output and the normal, or the light strength and the normal. And then we have our 3 positions, and we can just set those. So we don't need to keep resetting the normal because it's not going to change. And we should get the same thing. So we just cut out 4 extra lines of code because they weren't needed. They were just duplicates. I think that's most of it. We should be able to change the color because I added color. So let's make sure that works. I just kind of threw it in there, and who knows? Yeah. So we can change this color and make it do whatever we want. In the next video, we're going to be re-examining this color. I think we can do something to make it somewhat intelligible. When you actually apply this over like a more complicated mesh that is supposed to have a texture or something. I don't know if we're going to be using vertex colors. I don't think that would work, but I think we can do some tricks in order to actually look up texture colors that make sense, or at least get like a relatively good looking effect. So that's going to be next. If you have other ideas for what we can do here, or if you want to see like specular lighting get added on top of this as well, let me know in the comments. I would love to hear them. If there's other ideas for other videos you want me to do, or just questions you have, leave those in the comments, or come and join our Discord server and come and chat there. There's a link to that in the description, and I guess that's mostly it for now. So I will see you in the next video. Until then, see you, Internet.